The next topic we're going to cover, I'll use AsyncTask as an exemplar, but it's really more generic discussion about different kinds of frameworks. So we'll talk about the different types of frameworks, BlackBox Frameworks and WhiteBox Frameworks, and I'll show how AsyncTask actually embodies both types of frameworks within the abstractions that it exposes to the user. It's actually pretty cool. So first, let's talk about BlackBox Frameworks. A BlackBox framework only requires developers, app developers, people who use it, to understand the external interfaces or the external APIs of the objects. That's a black box framework. So it's a black box, right? You don't really know what's inside of it. Frameworks typically reuse a black box framework by parameterizing it or assembling it somehow. You typically give it something, like you give it a callback object, or you give it a pointer to a function or a method reference or something like that. And WhiteBox frameworks, in contrast, require some understanding of the framework implementation. In particular, you typically have hook methods that must be overridden by subclasses that extend or inherit from the framework. So that's a WhiteBox framework. So WhiteBox just means you have to be able to peek inside it and know a bit more about how it's designed internally. Each of these types of frameworks use different patterns. So if you remember 251, there's some different patterns. BlackBox frameworks typically apply patterns that emphasize extensibility via object composition. So classic examples would be the strategy pattern, where you make a strategy object and you instantiate the framework with that object. So it's like a black box. You give it an instance of something, and the framework will then call back on it somehow. Again, a lambda expression or a method reference or a callback object or whatnot. You give it an object. So strategy and decorator are good examples of patterns that work like that. In contrast, WhiteBox frameworks typically apply patterns that emphasize extensibility via subclassing. So here you're going to override the framework, or you're going to subclass the framework, and you're going to override one or more hook methods or primitive operations. So template methods, state, those are patterns that are often more widely used with WhiteBox frameworks. And one of the things that's interesting about the AsyncTask framework is it actually combines elements of both. So there's some things you can do by subclassing, and there's other things you can do by parameterization through giving objects and strategies. So let's talk about the WhiteBox elements of the AsyncTask framework first. So this enables long duration operations to run in the background and then interact with the UI thread in very stylized ways. And it uses the template method pattern to do this. So let's take a look here. When you call execute on an async task, that is the template method in the template method pattern. And then the framework dictates the control flow by making hook method callbacks at various points in time and in various contexts. So the first thing that will happen is the onPreExecute method gets called back in the UI thread, and that initializes stuff. Then the framework arranges to call the doInBackground method in a background thread, and that does some long-running task or operation. And then when it's done, it gives the results back to the user interface thread, and it does something with them, like displays them in the user interface. So you can see that these are callbacks that are dispatched when you call execute, and they take place in different contexts, but it's basically onPreExecute, doInBackground, onPostExecute. So those are well-defined hook methods that are called back. And you've got to know that this takes place. You've got to read the documentation. You have to understand that by subclassing AsyncTask, these are the hook methods you can override, and it will call you back at the right point in time and in the right context. This particular variant of the template method pattern allows the hook methods to run in different threads of control. And without getting too lost in the weeds, there's actually another pattern called the half-sync, half-async pattern, which we may talk about later in the class, and that's really what allows things to move back and forth between the threads. Let's now talk about the black box elements of the framework. So the AsyncTask uses black box framework elements to control the way that background threads are used to execute multiple async tasks concurrently. And it uses the strategy pattern in order to do this. So that's another gang of four pattern. There's some weird quirks. The default concurrency model for async task has changed over time. I won't talk about that right now. We'll cover that later. But for right now, just be aware that by default, everything runs, when you call execute, everything runs in the background one at a time. So it's serial background processing. If you don't want that, if you want to use something different, follow the next few minutes of the discussion. Okay, so you can configure the way the async task works by strategies that are handled or passed in to the framework, either by the way it's initialized or by strategies you can explicitly pass when you call execute on Executor. So by default, they use what's called the serial executor, and I'll show you what that looks like in a second. And what that does is the serial executor will have a single background thread, and all async tasks that are running within a process are executed one at a time in that one and only background thread. So that's the way it works out of the box. So it's nice. It lets you run the stuff in the background so you can do long-running blocking operations, but it is only one thing happening at a time. And here is what this looks like. So this is the code. If you were to go look at AsyncTask's implementation, which we will do later, you will see that there's something called the serial executor, and the one that's capitalized here is just an instance of serial executor. And serial executor implements executor, and so that means it has an execute method. And what it does is it makes a deck, non-thread safe deck of runnables, which it calls mtasks, and then it keeps track of which task is currently active. So when you call execute on an async task, what it'll do is it'll take that async task and it'll execute it. And what that does is it goes ahead and tries to enqueue a new runnable. I've shortened this a bit to use lambda expression. In reality, a bit more verbose, but it's the same concept. So basically, a runnable, the equivalent of a runnable lambda is created, and that runnable's run method, which is implicit in the lambda shown here, will call back the run method on the runnable passed in. So you can see we pass in R, and what this is doing is it's making a lambda expression, which when run, will run the runnable, and then it'll schedule the next thing to run. Okay, so that's what we're doing. We're enqueuing this runnable lambda expression into this deck, which is just a double-ended queue. And then if nobody else is running, we're going to go ahead and say start running the next item. Here's what schedule next does. So you notice that schedule next either gets called the first time if nothing's running, or it gets called after a runnable finishes running. So this is basically cooperative scheduling. What schedule next does is it tries to remove an item from the deck. If there's nothing in the deck, it's done. If there's something in the deck, then it says thread pool executor execute that runnable. And also kind of basically, well, it stores it so that we know that it's currently in the process of running. And so thread pool executor, we'll see what thread pool executor is in a second. That's just a thread pool that can run. But we're limiting this to only one thread running at a time. So one thread at a time is able to run in the background, and this code is ensuring that that takes place in a serial manner. Okay. Some applications need more than just serial processing in a single background thread. So imagine you're doing some kind of large-scale image processing operation where you've got to render a big image and you want to break it up into chunks, all the good stuff you would normally use concurrency and parallelism and multi-cores for. So in that case, you can call execute on executor, and you can pass in an executor that will do things in the background. So now we can have a pool of threads, and these threads can all run different instances of async task. So it allows multiple long-duration tasks to run in parallel within a process. So let's take a look at the code. And this is actually quite important because your next assignment requires you to do something like this, although don't do this because this is not what the requirements are, but it shows you what it does. This is the actual code for thread pool executor in the current version of Android. So what it does is it figures out the CPU count, which is the number of cores that your JVM knows about. So let's say that's 8 for sake of argument. It then figures out the core pool size, which is the CPU count plus 1, And it also computes the maximum pool size, which is twice the CPU count plus 1. So that would be, so this is going to be basically 9, and this would be, what, 17. We set keep alive to 1, which is going to be 1 second, as we'll see in a second. And then it makes a queue, a blocking queue of runnables that are linked together in a linked list of 128. That's the maximum size before the queue will block. And then the code creates a new thread pool executor. Thread pool executor is what you would pass in to execute on the executor. And that's going to be a new thread pool executor with core pool size default threads, which would be, in this case, equal to 9, if we had 8 cores, which can be expanded dynamically up to max pool size, which in this case would be 17. And the threads that are created dynamically, if all the other ones are in use, stay alive for 1 second before, if they're not used after 1 second, they're shut down. We are going to have this queue used to queue up to 128 async task objects if all the threads are busy doing other stuff. And we use this thing called a thread factory, which would be used to spawn the threads and give them a special name and so on. So this is what allows us to run all this stuff in parallel. So when you do your assignment, you will have to do something along these lines, although you won't use these exact parameters. You'll use other parameters that are described in the specification. So that's the place to look to figure out how to do this. And you'll be creating your own custom executor. So you could have your own custom executor, which in your case will be the being gazing executor or whatever you want to call it. OK, so you can pass that into execute on executor, whatever you want to have. And that's an example of the strategy pattern, because you're passing in a strategy that's used in a black box manner by the framework to run your threads in the background. And so that's a good example of the black box part of this whole thing. The async task is carefully designed to ensure that you don't have to worry about explicit synchronization in your code. It handles visibility issues and synchronization properly. And basically, you can set fields in the constructor or on pre-execute and safely refer to them in do in background without having to worry about memory visibility or race condition type of hazards. And likewise, when you're done in the background, you can execute fields in on post-execute, once again, without having to do any explicit synchronization yourself. That's done for you by the way the implementation works. OK, so that is the end of the async task framework discussion.